Hi, welcome to our last example. Example 4, solve a problem involving a linear quadratic system. So this is our last video for section 1.7, solving linear quadratic systems. All right, shout out to any of you if you have seen the movie Dudley Do-Right. Okay, um, I know this isn't really a very clear photo, but it's an old movie with Brendan Fraser. So he plays this RCMP who's always trying to do right by everybody, and he always seems to be messing things up. You can notice he's on the horse, and the horse is facing this way, and he's facing the other way, so he's already kind of off on the wrong foot. Okay, so in this question, it says Dudley Do-Right is riding his horse, that's actually his horse name, at his top speed of 10 meters per second toward the bank. And it is 100-meter away when the bank robber begins to accelerate from the bank, going in the same direction as Dudley Do-Right. The robber's distance d in meters away from the bank after t seconds can be modeled by this equation. So write a corresponding model for the position of Dudley Do-Right as a function of time. So we want to write something that gives his position with respect to time. Will Dudley Do-Right catch the bank robber? If he does, find the time and position where this happens. If not, explain why not. So let's get ready to kind of model this scenario. So let's just say the bank is right here, and the bank robber just leaves the bank. So the bank robber, okay, he's got a little bag of loot, a bag of cash there that he's running away with. So Dudley Do-Right, he's on his horse. Oops. That's not a bad horse. I've done a lot worse. Okay, so, oh no, that tail is terrible. Okay, let's try that again. There we go, that's better. I don't know, maybe not actually. Okay, so here is Dudley Do-Right. He's actually sitting on the horse the right way this time. Um, so it actually says he starts off 100 meters away when the bank robber begins to leave. So the bank robber starts here and takes off this way, and Dudley Do-Right starts off 100 meters away from the bank. And Dudley Do-Right can go 10 meters per second this way. So we now want to model an equation for that. So let's kind of write out some of this here. We'll probably also need to make an assumption too. Let's say that this is the origin right here. Okay. So let the bank be the origin. Okay, this means that Dudley starts at a position of negative 100 meters. Okay, negative 100 meters, because if this is 0, he starts off back here. So that's going left. That's a negative position. So he's actually starting off at a negative 100 meters. Okay, we also know he travels at 10 meters per second. Okay, so he's going this way, 10 meters per second. So that means his position could be equal to, he starts off at a negative 100, but then he's going 10 meters per second. So his position will be 10 meters times time. Okay, so you can see I've kind of set up this part here. This is like speed, and then we have time. So speed times time always gives you a distance. So if he's on his horse for let's say 10 seconds, he's going to go 10 times 10, he's going to go 100 meters. So that's actually when he'll reach the bank at 10 seconds. So that is part A. All right, part B. Will Dudley Do-Right catch the bank robber? If he does, find the time and the position where this happens. If not, explain why not. So the bank robber is actually accelerating. D equals to 0.2 t squared. He's accelerating this way. And Dudley Do-Right's already going pretty fast, so hopefully he can make it and eventually cut up to him somewhere down here before he starts going too fast and is never able to catch him. So we should do this by first equating both equations. So by both equations, I mean this one and I mean this one. So this is the robber's position, and this is Dudley Do-Right's position. So we'll do Dudley Do-Right first, and the other guy 0.2 t squared. So I'll have to subtract that on both sides. So minus 0.2 t squared, that will get rid of this. Whatever you do to one side, you got to do the other to keep it all balanced. So we got negative 0.2 t squared plus 10t minus 100. I'm just reordering this so that it looks like a nice quadratic. Square term, linear term, constant term. Now we need to go ahead and solve this. So before I decide which one I want to do, I'd like to get rid of that 0.2, that negative 0.2. Why don't we multiply by negative 5? Multiply by negative 5. The whole thing, both sides. Okay, we've got to do to both sides. So I'm going to multiply this by 5, negative 5, and this by negative 5, and that by negative 5. And when I multiply 0 by negative 5, I still get 0. So we will have negative 5 times negative 0.2 works out to 1. So we just have t squared. 10 times negative 5 is negative 50. And negative 100 times negative 5 is plus 500. And this is equal to 0. All right, this doesn't look factorable. 50 and 10 won't work. 25 and 20 won't work. So yeah, definitely not factorable. Let's go ahead. Let's apply quadratic formula. Let's apply quad formula. I just call it quad form for short. So we have t equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So we got a is 1, b is negative 50, c is 500. So we'll set those in. So minus negative 50 plus or minus square root negative 50 squared minus 4 times a is 1, and c is 500. All of that over 2 times a, which is just 1, so that'll just be 2. Okay, we have 50 plus or minus the square root. 50 squared is 2,500. And then 4 times 500 will give us 2,000. So we have minus 2,000 all over 2. 50 plus or minus the square root of 500 over 2. So it looks like we have two solutions. I'm going to go ahead and, since we know how to work with radicals, we're going to simplify that. We could do it off to the side. So we'll say root 500, that's equal to root 5 times 100. I usually write that the other way, the perfect square first, but we can take the square root of 100 and take that out. So we'll have 10 root 5. Okay, sometimes I even write these this way, root 5 times root 100. And then you can really see where the 10 comes from, right? So 10 root 5, let's plug that back in. 50 plus or minus 10 root 5 over 2. Notice I can easily divide these out by 2. That'll be 25, that'll be 5, and that is gone to just 1. So we have 25 plus or minus 5 root 5. All right, so that's the exact value. If I want to calculate the time and get an approximate, we could say, let me redo that here, approximate symbol. So let's do 25 plus 5 root 5, 36.2 seconds. And my other solution is going to be 25. Sorry, we'll type it in here. Decimal 25 minus 5 root 5. So that's 13.8. So you might say, oh, it's kind of weird to say, why are there two times? So these are the two times that they have the same position. So mathematically, what this means is the smaller one, that's when Dudley Do Right first catches the robber. So yay, he catches the robber. Um, Also, though, if we were to pretend that he didn't catch him and stop him, and that Dudley Do Right kept going, well, the robber is accelerating, and his speed is always increasing and increasing. So eventually, the robber would end up passing him. So this is basically a good example of the linear quadratic system having two solutions. And then that would be our time down here and distance up here. Okay, we can erase this here. So let's go ahead. Let's just do a final statement. So we can say, let's just double check what the question was asking for. It said, well, Dudley Do Right cuts the bank robber? He does. And if he does, find the time and position where this happens. Okay. So we can go ahead and state that. So we can say, yes, Dudley catches him at t equal to 13.8 seconds and a position of, so let's calculate what that position is. So we can use any one of these equations to do that. We can use Dudley Do Right's equation, or we could use the robber's equation. So I'm just going to pick Dudley Do Right's equation. And I'm going to do that off to the side here. We have d equal to negative 100 plus 10 times t. So negative 100 plus 10 times 13.8. So we have negative 100 plus 138. That gives us 38 meters. Okay, so he catches them at a position of 38 meters. All right, that's it for this video. I will see you next time.